All right, good morning, good Monday morning to all of you. We've been talking about NMR, and I wanted to spend just a minute telling you about where the splitting patterns come from. It's, whatever I tell you, it's going to be actually, reality's more complicated than that, but it's what I'll tell you is useful enough to help you understand NMR spectra. So we've been talking about peak shape and how, for example, if a peak is a doublet, that means a proton is adjacent to one and only one other proton. And so we're trying to figure out where this peak splitting comes from. And I told you to imagine that we're focusing in on proton A. That's sort of where we're standing, looking around the rest of the molecule. And the point was that the adjacent proton, that is a proton that's 3 bonds away on the adjacent carbon, can influence the magnetic field that proton A experiences, because of course proton B is itself a little magnet. And so one of the things that I told you from a few times ago was that in the presence of this external magnetic field, there's a difference in energy between being aligned with the field versus against the field. And that difference in energy is small enough such that it's still about 50-50 with versus against the field. So imagine we're looking at proton A and we're seeing what proton A experiences, and on average 50% of the time proton A is going to be near proton B, a proton B that is aligned with the magnetic field, the external field, and the other 50% of the time A is going to be next to proton B, where proton B is aligned against the magnetic field. This isn't in the same molecule, this is in different molecules. That is, in one molecule they'll be both aligned with, and the other molecule, HB, will be aligned against the magnetic field. And so on average, what you see in the NMR experiment is these two different populations of proton A. You see proton A that's adjacent to B that's aligned with the field, and proton A that's aligned adjacent to B against the magnetic field. And so what you see is this doublet. Okay, now if suppose we had our proton A and it was adjacent to 2 other protons. So here's A that we're interested in, and this time let's say there are 2 protons B. I don't know, we'll call them B and C, just, I don't know, that might be too confusing. We'll call them whatever. Protons B. Let's think of the possible situations in which proton A may find itself. This first proton can be aligned with the field or against the field, and the second proton can also be aligned with the field or against the field. So here are 3 different situations that proton A can find itself in. One is that it experiences the external magnetic field plus both of those adjacent protons aligned with that external magnetic field. So it's going to feel something that's a little bit stronger than the external magnetic field. On the other hand, it could experience one aligned with or one aligned against. And then finally, it could experience both aligned against. Okay, so 3 different situations. Now let's just think about things briefly. How many different ways can you have both adjacent protons aligned with the magnetic field? Just one, right? Same thing with against. What about one up and one down? How many different ways are there for that to happen? Twice, right? We could say this is proton B1, this is proton B2. You could have down, up, or up, down, right? So, weighted according to the probability of each of those situations, what you have is 1 way, 2 ways, and 1 way, or a 1 to 2 to 1 distribution of populations. So 3 different field strengths that proton A can experience, and twice as many ways to experience the one in the middle. So what you expect to see for this peak pattern is a 1 to 2 to 1 triplet. And we can go on for any arbitrary number of protons and figure out the probabilities. It just gets a little more complicated. So if you had 3 adjacent protons, I'll just set up the situation, though we won't go into all the details. You've got up, down, and up versus down. 3 different spin states, or 3 different possibilities. One where all 3 of these adjacent protons are aligned with the external magnetic field. One where all 3 are aligned against the magnetic field. And then a couple of different intermediate combinations for overall a 1 to 3 to 3 to 1 quartet. All right, so the idea is the nearby protons influence the kind of magnetic field a given proton itself experiences, and then that's that divides the signal up, the NMR signal, into various pieces. Yes?
And we should assume that all of those hydrogens are identical to each other and identical to the original one we're looking at, or just identical to each other?
So the question is, we should assume that all of these hydrogens are identical to each other and to the original one? No. Proton A is not identical to proton B. Protons that are identical to each other do not engage in splitting. Okay? So if we were to switch things around and say, okay, now I want to look at protons B over here, if they are identical to each other, they're not going to split each other. They will be split by an adjacent proton. All right. Yes?
So what determines the spin of a proton, and do they ever switch?
What determines the spin of a proton? Do they ever switch? There's 2 spin states that are allowed. One's with the magnetic field, the external magnetic field, the other's against. If there's no external magnetic field, then it doesn't matter. And so it's just 2 different energy states, and you can switch from one to the other with the appropriate amount of energy absorbed. All right, yes?
Is there a situation where, say, one of the protons goes with the magnetic field and there's 2 that go against?
Sure. So for example, in the situation where you're adjacent to 3 protons, you have actually 4 different situations: 1, 2, 3, and 4. The first is the proton experiences all 3 things adjacent, rather aligned with the external magnetic field. The other is it experiences all 3 against. And then you've got these 2 intermediate possibilities, let's say up, up, and down versus down, and down, and up. It turns out there are 3 ways to do each of those. Yeah. Yep, good. What else? All right, couple of things to know. Remember that when there are 2 different, the fact that the field experienced by proton A is slightly different here is the explanation for why you see peaks at 2 different chemical shifts or frequencies, okay? Because remember, the field a proton experiences is related to the energy difference between spin states, which is related to the frequency that will allow a transition between spin states, which is related to the chemical shift. You can measure the distance in chemical shift between 2 peaks. And that distance is called a J coupling constant. I don't know why they chose that letter. Talk to the physicists. But we'll call this JAB. That is the coupling constant, or the splitting constant between protons A and B. And just to make things worse for you, I told you that, with chemical shift we deal with units of ppm. With J coupling constants we could still stay with ppm, but the numbers are really small, so we go back to hertz because we prefer single-digit numbers that are easy to write. So we write these coupling constants in terms of frequency, really it's a difference in chemical shift between two peaks, but we turn it into a difference in frequency and we measure that in hertz, all right? And a typical coupling constant, the typical distance between peaks is about 7 hertz for protons that are adjacent to each other. That's not a number to memorize, and you almost never will be measuring coupling constants, but it can occasionally be useful. And the reason it's useful is because the coupling constants are, what's the right word? I don't know, reciprocal, meaning the splitting of proton A by proton B, 7 hertz, is going to be equal to the splitting of proton B by proton A. So you can sometimes tell in a spectrum which protons are adjacent to each other or coupled to each other because their splitting has to match. Okay? Maybe I'll show you an example, yeah, why not, of a situation where spin splitting can help you determine what's going on. So here is, we'll just put whatever here, we don't want to define that just yet. We've got 3 different kinds of protons here, A, B, and C. All right, so A and B are not identical to each other, and so they actually can split with each other. A and C are not identical, and neither are B and C. The relationship between A and C is they are that's not the right word, cis to each other. The relationship between C and B is that they are trans to each other. And then the relationship between A and B is they are on the same carbon, or another way of saying that is they are geminal to each other. And the double bond holds them in that specific orientation, and that can result in coupling constants that are really kind of large. So, for example, the trans coupling constant here ends up being around 15 hertz, whereas the cis coupling constant ends up being around 10 hertz. So let's pretend you are proton C, and let's imagine what this difference in coupling constants, the coupling constant between A and C is 10 hertz, between B and C is 15 hertz. So let's see if we can predict what we would expect to see for a proton that's adjacent to 2 non-identical protons, each with different coupling constants. In order to see this more clearly, let's go back to a simpler but related situation. Remember proton A adjacent to 2 identical protons? Another way besides doing this kind of thing that you can predict what the peak splitting pattern should be is like this. You say, okay, let's imagine the chemical shift of proton A is, there's some peak right here. And I'm imagining in my mind that I have turned off all of the splitting. You can actually do that in an NMR experiment, but for our purposes, oh, that's kind of fun. Kind of like a cowbell. Anyway, so let's imagine you can turn off the peak splitting pattern, which you can do in an NMR experiment, and then we're going to turn the peak splitting patterns on one by one. Okay, we're going to turn on the B1 splitting pattern. And let's suppose that the coupling constant between A and B is around 7 hertz, and that 7 hertz corresponds to this difference. Okay, so we turn on the splitting pattern for B1. That should split the peak for proton A into 2 peaks, 1 to 1, and the distance between the 2 of them should be 7 hertz. Okay. Now let's turn on the second splitting for the second proton. And again, the coupling constant between protons A and B, whether it's B1 or B2, is going to be 7 Hertz. So we're going to split each of these peaks here into their own doublets, again with a difference of 7 Hertz, right? But you see what happens, the second peak as it gets split overlays, whoops, as we split these two, there's overlap between the central peak and it doubles in height. That's another way conceptually you can think of peak splitting. This way may not be useful or it may be confusing to you. If you prefer to just think about it in the way we described it earlier, that's fine. But what this is intended to show you is the reason you see a triplet for proton A is because its coupling constant with the first proton is identical to its coupling constant for the second proton. All right? That's true in general when your two adjacent protons are identical to each other. But it's not always true. And you need to know that in order to understand what we're going to do next. Yes?
Can you repeat what you just said about identical constants?
Can I repeat what I just said about identical constants? No, forgot it. Sorry. The reason we see a triplet here for a proton adjacent to two other protons is because the coupling constant between A and B1 is identical to the coupling constant between A and B2. That's general when the two adjacent protons, B1 and B2, are identical to each other. If that weren't the case, if the coupling constants were different, we would see a more complicated pattern, right? So, any follow-up questions you want to ask about that? Why we, or what on earth I was doing here? Yeah.
Real quick, so with the sp3 hybridized carbon above, you said those two hydrogens were identical, but then with the sp2, like with the double bond, they weren't identical.
Yeah.
Why is that?
Okay, why are A and B not identical? But maybe we ought to just, well, no, it's too late. I've already made some bad decisions here in terms of what I've called these various protons. We'll just stick with them. Why are B1 and B2 identical here, but in an analogous situation, they're not identical there? Well, for one thing, it has to do with the overall symmetry of the molecule, but the short answer is rotation around this carbon-carbon bond allows protons B1 and B2 to interchange and experience identical environments. There's no such experience here because there's no rotation around carbon-carbon pi bonds. That being said, it may be useful to sort of pause and ask the question, what makes identical protons identical? Because if you don't believe A and B are not identical, if you believe they're identical, then anything I might tell you about the splitting pattern isn't going to make sense. So let's just take a brief moment and talk about what makes identical protons identical. And actually, this is where you want to dig out your knowledge and intuition that you got from Chapter 5, stereochemistry, because identical protons are all about symmetry. Okay? So, how many different protons in that molecule? There are 4 protons, but they are not different. They are identical because of symmetry, right? By rotation and movement of this molecule, you can interchange the positions of all of those protons. We're not going to go into the deep mathematical definition of symmetry. if you want to know more about that and point groups and stuff, you can take Chemistry 514. Okay, write it down. You'll get to it at some point. I actually didn't take it when I was here because I was biochemistry major and it wasn't required. But if you want to know more about it, you can take that. Let's see. How many different kinds of protons here? We'll use colors to indicate different kinds of protons. 3, 7, what? 2? Some of you were saying 2. Well, what about the proton that's coming out towards you versus going back in the page? They're the same. How? Why? Mirror symmetry. So 2 protons can be the same because of mirror symmetry, rotational symmetry, or pancake flipping operations or whatnot, right? So if the plane of the page is a mirror, proton in the back is identical to the proton in the front. By the way, methyl groups, how are those protons identical to each other? Because I can spin around a carbon-carbon bond to interchange their positions, and I can do that fast enough that on average you can't tell the difference between those 3 protons. All right? So symmetry and bond rotation are ways that, and then why are these protons here identical to these over here? Both adjacent to these 2 and by symmetry. The mirror plane that interchanges those 2 methyl groups is right here. See it? Okay. How many different kinds of protons are present in benzene? Who says 7? Somebody say 7? No? Okay. Well, what is it? Just 1. And there are multiple ways you can see, there are multiple planes of symmetry here. The element of symmetry that best explains why these protons are identical is what's called a C.3 axis of symmetry. You put the axis perpendicular to the plane of the page through that dot and rotate by 1/6 of a 360-degree rotation, and the protons are interchanged. All right. Let's see. Let's make it more fun, more challenging. Yeah, why not? I'm going to decide what might be useful. Okay, how about here? 2. Okay, sure. You're right. That's fine. Yeah, great. Good for you. How do you know those methyl groups are identical to each other? Plane of symmetry, wrong! It is not. I'm sorry, that was a little emphatic. I was waiting for you to do that. Sorry. Wrong. You lose, right. No, it is not a plane of symmetry. Why are those methyl groups identical? It's called rotational symmetry. The axis is right here, right there. It's called a C2 axis of symmetry. If you rotate by 180 degrees around this axis, we'll call this A, we'll call this B. Do that rotation, you get a molecule that looks exactly the same, only we've interchanged A and B. All right? So, some of what you've developed in Chapter 5 about stereochemistry and understanding the structures of molecules and symmetry is now going to be useful for you again in predicting the number and different types of protons in an organic molecule. All right, so let's go back to here, and, well, why don't we just say, How many different protons do I have there? 4. Okay. 1, 2, 3, and I guess we can't, it's bad to choose purple and pink because they look the same up on your screen, I guess. Green-ish. All right, why are blue and yellow or blue and orange different? There's no symmetry operation that exchanges the two, right? This is not a plane of symmetry. And it doesn't matter how you rotate or flip this molecule over, blue and pink are always cis to each other. Blue and methyl group are always trans to each other. There's no way to change that. They have permanently different environments. Okay? So there's more we could say about that. In particular, well, why not? It's fun. By fun, I mean you will encounter it again if you take Chemistry 353. So I'm going to tell you about it now, though I think you will hate it. Let's see. Why not? Okay, this is a molecule with a stereocenter. We'll put a star where the stereocenter is. It's pretty clear that this single CH group is its own thing. That's its own proton, right? The proton on the OH group is its own thing. It's pretty clear by symmetry that the green methyl group should be different from the blue methyl group because their connectivity is different. They're in different environments, right? How about the two protons adjacent to the stereocenter? This is a very difficult thing for students to see. You're used to thinking of CH2 protons as being identical, but remember, coming back here, the reason these two protons were identical was because you could exchange them via an operation of symmetry, whether that was a rotational axis or a mirror plane. Tell me about that with, we will call them, let's choose different letters, X and Y. Ooh, that's kind of fun. Tell me about X and Y and whether they're identical or not. Is there a plane of symmetry that allows me to interchange the positions of X and Y? Why not? Because of the pesky stereocenter, right? Imagine I pretend that the plane of the page is my plane of symmetry. If I ignore that pesky stereocenter and just cover it up, it looks like X and Y are reflections of each other. But in the presence of that stereocenter, they're not, right? There's no mirror plane of symmetry in this molecule. Another way of seeing that or talking about that is to say that X and Y are always going to have different environments. As the molecule is drawn here with the methyl groups in the plane of the page, X is on the opposite side of the molecule as this OH group, whereas Y is on the same side of the molecule as the OH group. Now, some of you may be saying, well, hey, I can fix that problem. Let's just rotate around carbon-carbon bonds, except we can't write the letter 3. The number 3, whatever. Okay, does that fix my problem? The answer is, sure, now Y is on the same side of the molecule or is on opposite side of the molecule as OH, but you had to move other stuff to get it there. And so it's not the same environment. Okay? Protons in general, in organic molecules, protons that are CH2 protons in a molecule that is chiral or that has a stereocenter are not identical. We will call these two protons, there's a special word for protons that are CH2 protons in a molecule that is chiral. We will call them diastereotopic, which is a term you will encounter in 353. Fortunately, I am not going to ask you questions. Are these two protons diastereotopic? I'm not going to ask that on your next exam, but I can guarantee you that Dr. Todd Bronson, my colleague, will ask you about that in 353. So you've heard it here, you're going to forget it, you're going to learn it again, and it's going to make more sense a second time. So just beware. Yeah?
So our definition of stereocenters previously was like 4 separate things connected to a carbon.
Uh-huh.
So if those protons are different, does that make that carbon a stereocenter?
That's a great question. If those protons are different, does that make that carbon a stereocenter? Oh man, wow, that's getting into philosophy, I think. And the answer is, in the NMR experiment, they are different. And this gets to a question of really what chirality means. I think what you're saying is, what you're noticing is, if a molecule is chiral, the whole molecule is chiral, not just the stereocenter. So what we say is a stereocenter has to do with our rules about assigning stereochemistry. Chirality is a more fundamental principle, and chirality is simply you're not the same as your mirror image. So yeah, we would still not call this a stereocenter, but I will tell you this. You don't want to know this. You really don't want to know this, but you asked. So there is something called prochirality, which is related to diastereotopic protons. And the idea is you can call this proton, one of them is pro-R and the other is pro-S, meaning if it was something different, that would be a stereocenter. You don't necessarily need to worry about it. I would not worry about it. You're right, we would not call that a stereocenter. Nevertheless, in terms of environment, these two protons are different, and they can show up with different chemical shifts. They might have the same chemical shift on accident, but in general, for diastereotopic protons, that is CH2s in chiral molecules, they can be different. Diastereotopic protons are we would also say that the blue and the yellow protons are diastereotopic. And the way you can think about this is to imagine a thought experiment where you label proton, the blue proton with some label that you can detect, and then you compare it to the situation where you label the other proton with something you could detect, and you ask yourself, what is the relationship between these two? And if they're diastereomers, the two protons are diastereotopic and are different. Okay? Now again, the biggest skill here is, can you identify protons that are not identical to each other? I don't care right now about what the term diastereotopic means. You are going to encounter it again when you take the organic lab, and you are going to hate it there. So if you want to save yourself some pain, spread out the hatred and take a minute to learn it now. But you won't see that kind of thing on my exam. However, you will need to be able to identify different kinds of protons. All right. Anything you want to ask about that?
Including ones that are on the same carbon.
I feel like now, given the amount of time we've spent on it in the past few minutes, it is a fair question for me to expect you to see that those protons are different. I won't ask you to tell me that they're diastereotopic. Okay. It may actually, if you don't believe that these two are different, that's okay. Truth doesn't actually care what you believe. Truth is truth, so yeah. But if you want, make a model of this molecule and just play around with it until you convince yourself that there is no way through rotation or symmetry to put X and Y in identical environments. All right, So we went through all of that just to convince you that that A and B here were not identical to each other. Now let's go back to the issue of coupling constants. And let's imagine what we see for proton, the peak for proton C, all right? And we're going to gradually, as we've done for the other molecule with the adjacent CH2 group, we're going to gradually turn on the adjacent couplings, okay? So let's first turn on JBC, which is the coupling constant between protons B and C, and it's worth about 15 hertz. So it looks like, if we're drawing everything to scale, it looks like 1 square is about 7 hertz. So a 15 hertz coupling constant would be something like this. All right, so if we turn on the coupling constant between B and C, we should get this 15 hertz spacing between the two peaks. Then let's turn on the coupling constant between A and C, which I told you was around 10 hertz. Okay, so that should be somewhere like this maybe. Now notice, because that second coupling constant is 10 hertz and not 15 hertz, the central peaks don't overlap. So instead of seeing a triplet, what you see is 2 doublets. This pattern is called a doublet of doublets, because you've got one doublet with a 15 hertz constant and a second doublet of a 10 hertz constant. So what you would see for this peak is just a 4-line pattern that looked something like this. And this is why you have to be smart when you're interpreting NMR spectra, because if you saw this pattern, you might be tempted to conclude, oh, these are 2 individual doublets, they must represent 2 different protons. But what I would tell you is this pattern is for a single proton, proton C. And if you did the integrated peak area thing, you would see this pattern of 4 peaks, and it would integrate for 1 proton, and then you'd be thinking, what on earth is going on here? And so be aware that if the coupling constants between adjacent protons are not identical, you may not see this conventional easy triplet pattern. You might instead see the doublet of doublets pattern. Yeah?
So in this example here, where you're splitting it first to 15, then to 2, like 2 tens,
Yeah.
it's because each time, like for each one, like for each like place where there's a 15, there's also a 10 effect coming in, and it can be positive, like plus
Right.
15, right?
That's right. Yeah, exactly. So yeah, the reason we see 2 lines, one split by 15, one split by 10, is because the influence of proton B on what C experiences is plus or minus 15. The influence of A on what C experiences is plus or minus 10. And so you have 4 different situations for proton C to experience. Up here, I don't know. Follow-up questions? I could say more about that, but I don't want to muddy the water. Yeah.
Is there anything other than a double bond that could change the coupling constant value?
Is there anything other than a double bond that could change a coupling constant value? Yes. Diastereotopic protons can couple with each other. And so if you have 2 diastereotopic protons and they're adjacent to only one other proton, you know, cross out what these methyl groups are. Fine. We'll just put benzene rings so that in this situation where you have a molecule that's chiral, 2 protons adjacent to the stereocenter, these 2 will couple with each other and with the adjacent proton. Coupling on the same carbon often has a very large coupling constant. So yeah, you probably would see for each of these a doublet of doublets. Don't expect you to predict that, but that's kind of what you're dealing with. Yeah?
When you're splitting
Do you always split with the largest coupling energy first? It's more convenient to do that, but you don't have to. Yeah.
Is there a way to sort of deduce, like, on your own, at least, like, which coupling constant would be larger across, non-identical?
Is there a way to deduce which coupling constant would be larger for non-identical protons? There are some rules of thumb. Across a double bond, trans coupling is larger than cis. For the case I just told you, geminal or same carbon coupling between different protons is bigger than adjacent coupling. But in terms of predicting actual numbers, no.
So they would just be given to us, like, on
Yeah. So at this point, rather than try to anticipate all the horrible possibilities, it's probably best to just start in with some examples. All right. So this is a fun one because it gives you some chemistry. And this is actually going to teach you something about a reaction you won't get to until 352. Let's use all the information we have. You're given this molecule, 4 carbons and a carbonyl group. Let's see, now that we've got the starting material, let's see, 1, 2, 3, 4, C4H something or other, 3, 5, 8. And then, let's see, we're given a mass spec number, and I'm kind of curious. I want to know, since I don't know what our reaction product Q is, but I do know that our starting material has this molecular formula. I want to try to figure out how the molecular formula changed as part of this reaction. And as we're doing this, I want you to pay attention to how I'm going about solving this problem. Some of you, when you're dealing with a problem that's unfamiliar, you kind of get stuck because you don't know where to begin, and you kind of want to see the end from the beginning. But that's not how science works. Scientists just get started. They start asking a question, and they just get going and try to figure it out along the way. So don't worry if you can't look at that spectrum and say, I know what that is, because nobody can. This is science. We use the data to figure stuff out. So what I'm asking is, how did the molecular formula change when I went from here to whatever this is? I've got some clues here, and if you know a bit about what's going on in 352, this is actually really easy, but you don't know that yet. So let's try to see how many mass units were added to this molecule. So C4H8O, you guys do the arithmetic because I'm too lazy. Well, now there's a controversy, so somebody's got to figure it out. So 62, 72, it's 72? Okay. Somebody's muttering, it's still 62. Okay, fine. You really want me to get my calculator out? Carry the 5, yeah, okay. So how many mass units did I add going from here to here? Okay, so this product is plus 14. All right. So what would account for plus 14? Okay, you could add 14 hydrogens, but probably not. Good luck with that. You could add a nitrogen or a carbon and 2 hydrogens overall. Okay, good. Now, what does this IR peak tell us about product Q? Still got the carbonyl group. Okay, still got the carbonyl group. All right. So, good. Let's move on from there. Actually, let's go ahead and pretend if we know, let's go ahead and pretend, frankly, because there's no nitrogen in any of the products, we probably want to rule out the adding a nitrogen. So if we added a CH2 group, our new formula would be C5H10O. Okay, run that through your double bond equivalence or degrees of unsaturation, and that tells you how many double bonds we got in this thing? Just one, right? One double bond, one pi bond or ring, 1 degree of unsaturation, and we've already accounted for that in our carbonyl group. All right. So those are some of the parameters we're dealing with. Now let's look at the NMR spectrum. We see 3 peaks. We see one that's 6 protons. We see one that's 3 protons, and we see one that's worth 1 proton. That's integrated peak area. The authors of this problem were nice to you. They didn't require you to look at dimensionless and arbitrary peak units, peak area units, and have you figure out the ratio between peaks. They just said, we feel bad for these folks, let's give them something. And so you know that this peak represents 1 proton, this is 3, this is 6. By the way, that actually is consistent with what we said our molecular formula might be. Okay, so now let's look at the splitting pattern. Let's start with this 3 proton peak. What substructure in organic molecules do you know of where you can have 3 protons that are identical to each other? The methyl group, good. And what shape of a peak is this? Okay, it is a 1-to-1 doublet. No, you're right, sorry. That's right. So, yes, this is a methyl group. It is a singlet. That tells you whatever it's bonded to, no protons. Okay? How about this one? 1 proton, how many peaks are there? 1, 2, 3, 4, 5, 6, 7. That's a 7-line pattern. If you wanted to analyze those peak heights, and if you wanted to run Pascal's triangle out to the level n equals 6, you probably would come to that pattern. How many adjacent protons should be there? Yeah, roughly 7-line pattern. A good guess is 6. The reason we're guessing that is because we happen to have over here a 6-proton signal that is, in this case, a 1-to-1 doublet. So, this is a single proton adjacent to who knows what, but whatever there are 6 protons. This is, how many methyl groups could 6 protons be? Yeah, I can't think of any other way than 2 identical methyl groups to have 6 identical protons, except for perhaps benzene, which we know this isn't that. So, all right, 2 identical adjacent methyl groups. What do these methyl groups have to be next to? Just 1 proton. You know that because they're doublets. So far, are our data internally consistent? Gotta be, because we just saw the 2 methyl groups that are being split by the 1 proton, and now we have that same 1 proton being split by the 2 methyl groups. You now have enough to solve this problem. I think this is the point at which we hear the dung-dung, and then we roll credits, and we have to wait till next week to see what the solution is. All right, figure it out, solve it. You can do it.